Hi everyone. In this video, we're going to introduce the idea of a circular function. So we're not going to get into the nuts and bolts as to how to compute certain values and properties of these functions. We just want to understand what it means to take properties of a circle and associate them with a function. Now, you may have been told in previous classes that the graph of a circle does not constitute a function. It's a famous non-example of a graph that's not a function. And that's correct in the sense that for every, usually for functions, our x inputs are, our x values are inputs and our y values are outputs. So given some x value, we have like two different y values associated with it, and every x value should only have one output to go with it. So that sort of ruins the idea of the graph of a circle being a function. So when we talk about circular functions, that's not what we're talking about. What we're talking about is associating one property of the function with an input and one property of a function with an output. So here I've made this Desmos graph that will help illustrate this, and it will also be made available to you in D2L to for you to play around with and change its parameters and to help you work through the first set of activities. So what we have is a Ferris wheel, um, as described in the very first preview activity. Its radius is 150 meters. So from the ground to the center is 150 meters. From the center to the top is 150 meters. That's 300 meters height as you can see here. And so right now we have a car or cart, whatever it's called, sitting on the bottom of the Ferris wheel. It hasn't traveled at all yet, so the distance traveled is zero, height zero, right? It's sitting on the bottom. And so what we want to note is that as we go forward, you start to travel some, right? Like as you go around the Ferris wheel, you start to travel some amount of distance, and you start to gain some height as you're going up at first. And so you're gaining some height, you're gaining height as you go forward. And what we see here in this black curve is an x value that represents the distance we've traveled so far along this. This blue dotted line is the path you've taken so far on this Ferris wheel. And the height is how high you are, right? It's how high off the ground you are. And so you can see the height here, you can see the distance traveled here, right? The distance traveled is if I took the curve along the wheel and I flattened it out, right? Just to see raw distance, how far we travel. And we keep traveling and we keep traveling and we keep traveling and we keep traveling. And at some point, we're going to hit the top of the Ferris wheel, right? After we've traveled halfway around the circle. And after that, we're going to keep traveling downwards. Now we're traveling further, right? We're going around. And so our distance is increasing, how far we've traveled, but our height's now decreasing. And you can see that in this part of the curve here. We keep traveling, we keep traveling, we keep traveling, we keep traveling, we keep traveling. And we hit the bottom of the Ferris wheel. And at this point, we've traveled all the around the the Ferris wheel. So 2 pi times the radius, and we're back to height basically zero here. So what you get then, if we ignore the graph of the wheel, what we get is a graph of the relationship between the distance traveled and the height that you achieved while doing this. So you can think of equivalently this as a graph of time or something, but that curve here certainly represents a nice, well-defined function. The distance as an input and the height as an output. And so I capped this cycle at going around once, right, for 2 pi. But you might imagine that you could keep going, right? You could travel another way around the circle. So then this graph here would go another cycle up and down again, and then up and down again, and then up and down again. If we wanted to keep going around and around in the circle, I only capped it at one time around the circle because I figured that would illustrate everything that's going on. So hopefully that illustrates why we can think of the height as a function of the distance, the height around a circle, or the height as you go up and down in a circle, as a function of the distance traveled on the circle. And you might imagine that this sort of idea could be applied to any circle, not just this particular Ferris wheel example. So let's set our thing back to 0. What you see here is a folder called parameters. If I open it up, I could change, say, the radius of the circle I want to look at, and I can change the x and y values. Let's make the x value a little bit bigger, of the center of the circle. So if I do that, then this is my circle now. Its center has x value 6 and y value 8, so that's the center there. And the radius is 4, so that's what I set it to. But still, if I go ahead and traverse around the circle, right, I go some height up and down. And I travel some distance as a result, right? And so for every, as I move my distance forward, my height goes up, it goes down. The height that I'm at is still a function of the distance. All right. Thank you very much. I'll see you in the next video and in the discussion boards.